power in watts of a lamp is given by the equation P equals V times I, where P is the power in watts, V is the voltage in volts, and I is the current in amps. If a lamp is rated at 100 watts or 130 volts, then 100 watts equals 130 volts times I. Solving for I, we get I equals 100 watts divided by 130 volts, which equals 0.769 amps. If the same lamp is supplied at 120 volts, we need to determine the new current. Since the resistance of the lamp remains constant, we can use Ohm's law to find the new current. However, a simpler approach is to recognize that the current will change proportionally with the voltage, assuming the resistance of the filament remains relatively constant. Therefore, the new current will be I equals 120 volts divided by 130 volts times 0.769 amps, which equals 0.722 amps. And the power will be P equals 120 volts times 0.722 amps, which equals 85 watts. Therefore, the same lamp will put out 85 watts if supplied at 120 volts. Let's delve a bit deeper into the relationship between voltage, current, resistance, and power in this scenario. Firstly, it's important to understand Ohm's law, which states that voltage equals current times resistance, or V equals I times R. Secondly, the power formula P equals V times I can be rewritten using Ohm's law to express power in terms of voltage and resistance, or current and resistance. Specifically, P equals V squared divided by R, and P equals I squared times R. In the initial scenario, the lamp is rated at 100 watts and 130 volts. We calculated the current to be 0.769 amps. We can also calculate the resistance of the lamp using Ohm's law or the power formula. Using Ohm's law, R equals V divided by I, so R equals 130 volts divided by 0.769 amps, which equals approximately 169.5 ohms. Alternatively, using the power formula P equals V squared divided by R, we can rearrange it to solve for R equals V squared divided by P, so R equals 130 volts squared divided by 100 watts, which also equals 169 ohms. Now, when the lamp is supplied with 120 volts, we assume that the resistance remains constant at 169 ohms. Using Ohm's law, we can calculate the new current I equals V divided by R, so I equals 120 volts divided by 169 ohms, which equals approximately 0.71 amps. Then, using the power formula P equals V times I, we can calculate the new power P equals 120 volts times 0.71 amps, which equals approximately 85.2 watts. Alternatively, using the power formula P equals V squared divided by R, we can calculate the new power P equals 120 volts squared divided by 169 ohms, which also equals approximately 85.2 watts. The slight difference in the current and power values calculated using the two methods is due to rounding errors. In practice, the resistance of a lamp filament does change slightly with temperature, which affects the accuracy of these calculations. However, for most practical purposes, assuming a constant resistance provides a reasonable approximation. In summary, when the voltage supply to a lamp is reduced, the current also decreases, resulting in a lower power output or wattage. The relationship between voltage, current, resistance, and power is governed by Ohm's law and the power formula. By understanding these relationships, we can predict how a lamp's performance will change under different voltage conditions. To further elaborate, let's explore how temperature affects the resistance of the filament. The filament in an incandescent lamp is typically made of tungsten. Tungsten's resistance increases with temperature. When the lamp is operating at its rated voltage of 130 volts, the filament reaches a certain temperature and its resistance is 169 ohms, as we calculated. When the voltage is reduced to 120 volts, the filament cools down slightly and its resistance decreases somewhat. This decrease in resistance means that the current will be slightly higher than what we calculated assuming constant resistance, and the power output will also be slightly higher. However, the change in resistance is usually small enough that it doesn't significantly affect the overall power output. For more precise calculations, we would need to know the temperature coefficient of resistance for tungsten and the exact temperature of the filament at both 130 volts and 120 volts. This information is usually not readily available, so we typically assume constant resistance for simplicity. Another factor to consider is the type of lamp. The calculations we've discussed apply primarily to incandescent lamps. Other types of lamps, such as LED lamps and fluorescent lamps, have different characteristics and may not follow the same relationships between voltage, current, and power. LED lamps, for example, typically have a driver circuit that regulates the current flowing through the LED. The driver circuit attempts to maintain a constant current, even if the voltage fluctuates slightly. Therefore, the power output of an LED lamp may not change as much as an incandescent lamp when the voltage is reduced. Fluorescent lamps also have a ballast that regulates the current. The ballast ensures that the current remains relatively constant, even if the voltage varies. However, if the voltage drops too low, the ballast may not be able to maintain the current, and the lamp may flicker or not light up at all. Furthermore, the calculations we performed assume that the voltage is alternating current or AC. If the voltage is direct current or DC, the calculations are the same, but the behavior of some types of lamps may be different. For example, some LED lamps are designed to operate on either AC or DC voltage, while others are designed to operate on only DC voltage. It is essential to check the lamp specifications to ensure that it is compatible with the type of voltage being supplied. Additionally, the power factor of the lamp can affect the accuracy of the power calculations. The power factor is a measure of how effectively the lamp converts electrical energy into light. A power factor of 1 indicates that all of the electrical energy is being converted into light, while a power factor less than 1 indicates that some of the energy is being wasted as heat. Incandescent lamps typically have a power factor close to 1, while LED lamps and fluorescent lamps may have a lower power factor. If the power factor is significantly less than 1, the power calculation should be adjusted to account for the wasted energy. The apparent power, measured in volt-amps for volt-amps, is the product of the voltage and the current. The real power, measured in watts, is the actual power being consumed by the lamp. The relationship between apparent power, real power, and power factor is given by the equation real power equals apparent power times power factor. In summary, when calculating the power output of a lamp at different voltages, it is essential to consider the type of lamp, the voltage type AC or DC, the temperature coefficient of resistance, and the power factor. For most practical purposes, assuming a constant resistance and a power factor of 1 provides a reasonable approximation for incandescent lamps. However, for more accurate calculations, especially for LED lamps and fluorescent lamps, it may be necessary to consider these additional factors. One more thing to consider is the potential for harmonic distortion in the electrical system. Harmonic distortion can occur when nonlinear loads, such as electronic devices, draw current in a non-sinusoidal manner. This non-sinusoidal current can create harmonic voltages and currents that distort the voltage waveform. Harmonic distortion can affect the accuracy of power measurements and can also cause other problems in the electrical system, such as overheating of transformers and conductors. To mitigate the effects of harmonic distortion, it is essential to use appropriate filtering techniques and to ensure that the electrical system is properly designed to handle nonlinear loads. In the case of a lamp, harmonic distortion is usually not a significant concern, especially for incandescent lamps. However, some LED lamps and fluorescent lamps may generate some harmonic distortion. If harmonic distortion is a concern, it is essential to use a power analyzer to measure the harmonic content of the voltage and current waveforms. The total harmonic distortion, or THD, is a measure of the amount of harmonic distortion present in a waveform. A lower THD indicates less harmonic distortion. In addition to harmonic distortion, voltage fluctuations can also affect the performance of a lamp. Voltage fluctuations can be caused by various factors, such as changes in the load on the electrical system, switching of large loads, and faults in the electrical system. Voltage fluctuations can cause lamps to flicker, dim, or even fail prematurely. To mitigate the effects of voltage fluctuations, it is essential to use voltage regulation devices such as automatic voltage regulators or AVR. An AVR can maintain a constant voltage output even if the input voltage fluctuates. This can help to improve the performance and lifespan of lamps. Finally, it is important to consider the safety aspects of working with electricity. Always disconnect the power before working on any electrical equipment. Use appropriate safety gear, such as insulated gloves and safety glasses. Follow all applicable electrical codes and regulations. If you are not comfortable working with electricity, consult a qualified electrician. Electricity can be dangerous, and it is essential to take precautions to protect yourself from electrical shock and other hazards. When working with lamps, it is also important to handle them carefully. Some lamps, such as incandescent lamps, can become very hot and can cause burns if touched. Allow the lamp to cool down before handling it. Also, be careful not to drop the lamp, as it can break and create a hazard. Dispose of broken lamps properly. Some lamps, such as fluorescent lamps, contain mercury, which is a hazardous material. Dispose of these lamps according to local regulations. In summary, calculating the power output of a lamp at different voltages involves understanding the relationships between voltage, current, resistance, and power. It is also essential to consider the type of lamp, the voltage type, the temperature coefficient of resistance, the power factor, harmonic distortion, voltage fluctuations, and safety aspects. By taking all of these factors into account, you can accurately predict the performance of a lamp and ensure that it operates safely and efficiently.